Beneath the frozen soil of Russia's Far East, a monumental feat of modern engineering rises like a titan against the horizon. At the sprawling Vostochny Cosmodrome, elite engineers lay the complex foundations for humanity's next giant leap into space. The MIK-RN complex is a mammoth industrial cathedral designed for the high-stakes assembly of advanced deep space vehicles. Spanning 28,000 square meters, the facility utilizes reinforced concrete to withstand ultimate mechanical stresses and vibrations. Massive steel pillars are driven deep into the permafrost, utilizing thermal technology to ensure the structure remains perfectly level. Here, in this remote oasis, Russia constructs the cutting-edge assembly line for the legendary Orel spacecraft, a next-generation lunar vessel. Engineers monitor the pouring of special heavy-density concrete with precision, ensuring the floor supports the weight of future rockets. Every structural pillar is a masterpiece of physics, required to bear thousands of tons of weight without a micron of deflection. The scale of the main hall is breathtaking, a vast space echoing with the sounds of industrial metalwork and focused activity. Huge overhead cranes, lifting 200 tons with grace, span the entire ceiling on massive rails with fine-tuned electronic precision. These heavy gantries move monumental rocket stages and reinforced ship hulls through the various complex stages of the assembly process. Special climate control systems maintain steady atmosphere and humidity, preventing expansion of sensitive metal components in extreme Siberian weather. To build a spacecraft for the vacuum, you must first master the physics of heavy metal and the molecular behavior of alloys. Massive sheets of advanced aluminum-lithium alloy arrive from the Urals, prized for their incredible and durable strength-to-weight ratio. These advanced materials offer lightweight properties essential for fuel efficiency, coupled with tensile strength to protect the crew during launch. The raw alloy sheets are fed into giant precision rollers, which apply millions of pounds of pressure to bend the metal. These curved segments will eventually form the main crew capsule, the pressurized sanctuary where humans will live during the transit. In the specialized welding bay, advanced robotic arms prepare for the primary join, calibrating sensors for maximum structural safety integrity. Friction stir welding, a state-of-the-art process, joins the alloy plates without melting them, preserving the original crystalline metal structure. This technique ensures seamless, molecular-level strength along every single seam, creating a hull with no weak points for potential leaks. An automated welding head glides along the metallic dome, monitored by high-speed cameras and sophisticated real-time ultrasonic scanning sensors. Intense localized heat binds the aerospace alloy plates into one unified body, capable of withstanding the immense pressure of orbital vacuum. Senior engineers oversee the process from a shielded, high-tech control cabin, analyzing live data streams and thermal imaging results. Every welded seam on the Orel spacecraft undergoes rigorous, automated quality scan procedures involving multiple layers of non-destructive structural testing. High-energy X-ray scanners move along the joints, searching for microscopic structural defects that could compromise the safety of the mission. The stakes are high, as even a microscopic fissure could cause catastrophic decompression in the harsh, low-pressure environment of space. Once the inspection is complete, the pressure hull is slowly lifted off the assembly jig, appearing as a shining engineering jewel. This gleaming metallic sphere represents the ultimate shield for the future cosmonaut crew, a bubble that must withstand radiation and cold. Next, the heavy structural ring of the service module is prepared, acting as the primary interface between the capsule and rockets. This solid titanium ring, machined from a single block of metal, is designed to distribute massive thrust loads across the frame. Hydraulic presses with immense force stamp out the structural ribs of the ship, creating the internal framework that provides necessary rigidity. These internal ribs act as the structural bones, preventing the lightweight metal hull from buckling under gravitational stresses during launch. Highly skilled workers align each structural frame inside the cylindrical body of the service module, working with extreme mechanical assistance. Precision lasers project bright red alignment lines onto the metallic walls, guiding the assembly team to ensure every part is positioned. Every fastener must be tightened to an exact, calibrated torque specification and recorded in a digital log for maximum mission reliability. This meticulous assembly process creates the rigid skeletal network of the spacecraft, a masterpiece designed to survive the violent launch phase. Outside the main hangar, massive diesel generators stand ready, providing critical backup industrial power to ensure the build process continues. The electrical grid of this facility could support a city, fueling the energy-hungry lasers and cranes required for spacecraft manufacturing tasks. Inside the hull, advanced electrical wiring harnesses containing miles of cabling are slowly routed through dedicated internal service channels. These specialized cables are the nervous system of the Orel, designed to transmit critical telemetry data and life support power. Each wire bundle is wrapped in protective gold-colored thermal foil, which reflects radiant heat and protects electronics from extreme temperatures. Engineers perform thousands of individual continuity tests to ensure flawless signal transmission, checking the integrity of every single wire connector. There is no room for error, as a single faulty connection could cause complete system failure during the critical launch sequence. Next, the massive thrust cone of the spacecraft, which bears the engine forces, is slowly positioned for final module integration. This structural cone is a complex hub housing the docking system, communication arrays, and the steering thruster networks for maneuvering. These thrusters maintain the precise orientation of the vessel during the complex and dangerous process of docking with the station. The alignment of the steering nozzles must be exact to 1/10 of a degree to ensure fuel efficiency and safe operations. Specialist welders join the high-pressure propellant lines with absolute focus, working in cramped quarters with the extreme precision of surgeons. These lines are the arteries of the ship, carrying volatile fuel and oxidizers to the engine systems under immense internal pressure. Every single plumbing joint is welded inside a sealed argon gas chamber to ensure the absolute purity of the weld. The use of inert argon gas prevents oxygen from degrading the titanium welds, ensuring the joints remain strong under propellants. Next, the massive composite heat shield plates are carefully prepared in a cleanroom environment to prevent any contamination before bonding. This heat shield is the ship's only protection against the inferno of re-entry, where air friction generates temperatures exceeding 2 to 1,000 degrees. Each individual carbon-carbon tile is meticulously bonded to the capsule base with high-temperature adhesive, a process taking weeks of labor. Workers verify the gap between each individual tile using thickness gauges, ensuring there is enough room for thermal expansion. The tiles are designed with thermal expansion in mind, allowing them to expand under high heat without crushing one another. A specialized protective coating is sprayed evenly over the heat shield assembly, providing an extra layer of protection against atmospheric elements. This dense chemical layer is essential for preventing moisture absorption into the porous tiles, which could lead to structural cracking. With the exterior hull complete, work moves to the capsule interior layout, where ergonomic needs meet high-tech digital flight systems. The aluminum structural frames for the cockpit consoles are firmly anchored to the internal ribs, providing a stable instrument platform. These solid frames will soon support the glass cockpit control screens, providing the crew with a high-resolution interface for monitoring. Heavy-duty, shock-absorbing mounts, engineered to dampen the violent forces of landing, are installed beneath the locations of the seats. These mechanical dampers are a critical safety feature, designed to protect the human crew from extreme landing impacts on land. High-pressure oxygen tanks are carefully slotted into the lower compartment and secured with multiple redundant locking mechanisms for maximum safety. The titanium spheres holding the breathing gas are wrapped in dense composite layers for safety, ensuring they remain intact during stress. Plumbing for the advanced air scrubbing system is routed along the walls, a complex network of pipes that cycle cabin air. These specialized canisters remove carbon dioxide and contaminants, keeping the cabin air perfectly breathable for the crew during the mission. Each pipe connection in the life support system must be verified through pressure tests to prevent trace gas leaks in cabin. The spacecraft's main electrical bus is now linked to the main battery array, completing the power circuit that runs systems. These high-capacity chemical cells store massive amounts of energy, providing necessary power for the long transit phases of the mission. Engineers monitor power distribution diagnostics on specialized software screens, checking the health of each cell and the efficiency of regulators. Voltage fluctuations must be strictly minimized to protect sensitive navigational computers and delicate sensors from any potential electromagnetic power surges. Next, the massive solar panel deployment mechanisms are meticulously checked for mechanical smoothness and absolute reliability in the orbital vacuum. The spring-loaded hinges must unfold smoothly and lock into place, where there is no air to dampen the wing movement. A laser measurement system tracks the alignment and speed of the panels, ensuring they deploy without putting stress on the module. With the solar tests complete, the wings are carefully folded back into their compact launch configuration, tucked behind protective fairings. Protective carbon fiber shells are bolted over the sensitive solar cell panels, shielding them from acoustic vibrations and extreme launch heat. Now, the finished crew capsule must be joined with its heavy service module to create the integrated flight vehicle for space. Overhead cranes align the two massive structures with absolute physical precision, moving them closer while technicians watch every structural gap. Engineers guide the final descent of the capsule onto the service module, ensuring every electrical and fluid connector is securely aligned. Heavy-duty steel tension bolts are threaded and tightened to lock the modules together into a single, unbreakable unit for flight. A specialized collar seal at the interface is pressurized to verify the structural integration and ensure no air can escape. This combined assembly represents the complete core of the new spacecraft, a masterpiece of engineering ready to face the space environment. Now, the ship enters the most brutal testing phase, a period of shake, bake, and freeze that pushes components to limit. A massive transporter shifts the entire vessel from the assembly hall to the environmental test bay for final certification and approval. The ship is slowly guided inside the colossal stainless steel vacuum chamber, a high-tech fortress designed to simulate the airless void. This chamber, known as MIKDK, is one of the largest in the world, capable of reaching pressures found in Earth orbit. The multi-ton airlock door is slowly swung shut and sealed with industrial clamps, creating an airtight environment for the stress tests. Heavy-duty industrial vacuum pumps begin their deep hum as they start the hours-long process of removing all air from the chamber. Atmospheric pressure inside the chamber drops rapidly, simulating the ascent of the ship as it leaves Earth and enters orbit. The spacecraft structure expands and contracts slightly as the air pressure vanishes, testing the integrity of every seal and material connection. Thermal testing arrays inside the chamber activate, blasting the hull with extreme radiant heat to simulate the direct energy of sun. These intense heat lamps simulate solar radiation, which can heat the sunward side of the ship to hundreds of degrees. Next, liquid nitrogen lines flood the chamber walls, dropping internal temperatures to freezing to simulate the cold shadow of the Earth. This rapid thermal cycling stress tests every material and electronic component, ensuring they can survive the constant temperature shifts of orbit. Inside the control room, banks of diagnostic monitors trace every critical parameter, from structural strain to the health of battery systems. Every single sensor on the ship must remain active and transmit clean, accurate data throughout the test, proving systems operate flawlessly. After days of simulated orbit, the vacuum chamber is slowly repressurized, allowing the ship to return to ambient conditions for inspection. The massive steel door swings open, releasing a cloud of cold condensation vapor as the hangar air meets the test chamber. The spacecraft emerges unscathed, its hull gleaming and systems green, proving its structural integrity to the dedicated team of elite engineers. Now, the finished vehicle is prepared for final electrical and RF integration, focusing on the communication systems that link to Earth. Specialized non-reflective foam spikes line the walls of the anechoic test chamber, creating a space free from any radio interference. This specialized room absorbs stray radio waves, creating a completely silent environment where antennas can be tested without any electronic echoes. Engineers test the spacecraft's transmitter antennas, measuring signal output strength and beam patterns to ensure they communicate across thousands of miles. The navigation systems must successfully lock onto simulated GPS and GLONASS signals, proving the ship can find its position with accuracy. The telemetry transmission remains clear and unbroken throughout the grueling test, confirming the data links are robust enough for the mission. With the electrical integration fully verified, the craft is prepared for the long transport to the launch pad, where journey begins. Heavy protective transit tarpaulins are carefully draped over the delicate composite parts and the shining hull to protect from dust. The vehicle is secured onto a massive, heavy-duty multi-axle railcar platform designed to carry the spacecraft with minimal vibration over rails. This specialized rail system, a vital artery of the space program, connects the manufacturing facility directly to the launch complex. Powerful locomotives pull the precious cargo slowly across the vast Siberian expanse, moving at a measured pace to ensure vessel safety. The logistics chain requires perfect timing to navigate the frozen terrain, ensuring the ship arrives at the pad for launch. At the Vostochny launch site, the spacecraft is rolled into the preparation hall for the final countdown procedures and fueling operations. The protective transport covers are carefully unbolted and removed, revealing the completed, silver-skinned hull of the Orel, ready for flight. This moment represents the pinnacle of decades of Russian aerospace engineering and the culmination of work by thousands of dedicated professionals.
From right here inside the integration hangar, the structural integrity of the main rocket components is being tested before rollout. It's an intricate process. We are standing inside the largest hangar in Europe, home to the Starseeker project. The scale of this spacecraft is simply breathtaking. The successful integration of the core stage means we are just weeks away from the scheduled launch, a monumental step for the agency.
Subscribe to TechFlow Manufacturing for more exclusive, in-depth breakdowns of monumental engineering and the machines that are shaping our future civilization. This is a triumph of human intellect and perseverance, a machine built to conquer the deep cosmic void and light the way.